Welcome to 1007 ICT, 1807 ICT, 7611 ICT, Computer Systems and Networks. This is Lecture 9, Packet Transmission. So last time we covered the idea of computer communication, OSI model, TCP/IP, and we led into the different layers for these models. There were 7 layers in the OSI model. We looked at some network topologies and then some network categories, just to kind of give a sense of, how when we build networks, what they might look like and how they might be connected, and some of the attributes of some of those networks. Like if it's a local area network, it has a certain kind of attribute. If it's a wide area network, it has slightly different attributes. So in this lecture, we're going to look at the data link layer, addressing, transmission errors, and medium access control. So again, we're going to have gained an understanding of these things. There's lots of concepts. Any of these things you could drill down fairly deeply into. There's a lot of detail there. We're just going to look at the high level, where it kind of fits and what it's about. So the data link layer, you'll see there, that's the second layer just above the physical one. So it's still really close to the hardware. Right, it's not at the user level, for example. It doesn't care about text input and all those kinds of things. So the data link layer is responsible for ensuring that a frame of data is successfully transmitted between 2 adjacent nodes in the network. And you'll see, typically we tend to, at this level, talk about packets or frames or chunks of stuff or chunks of data. They do have a particular name at each level. We may sort of gloss over that name, use just packet or frame or whatever, but there is a specific name at a particular level, I should say. So just bear that in mind. So this level is called a frame, and it's transmitted between 2 adjacent nodes. So the data link layer attempts to make the physical layer appear error-free to the layers above it. All right, so it also looks at controlling the node-to-node, or me and my neighbor delivery. So it looks at access control, so deciding when a device connected to the link can transmit, basically who gets to talk and when. Framing, it works out, well, what's the start of this frame and what's the end of the frame, how big is it basically, and what's inside it. Where is the address? If I'm going to talk to someone, I need to know who I'm talking to, right? So it has a particular place. The addressing, so the address of the next node along the route to the intended final destination. That may be the final destination, it may not be. If it's not the final destination, it has to get to them first, and then they do the same process, right, to make sure that it propagates to the end node. Error control, so there may be some errors for detecting and recovering from transition errors between 2 adjacent nodes. So this is not the overall message path, it's just between me and my neighbor. There may be some things that go wrong. And then flow control, that prevents the receiver from being swamped by timing the release of the data. So you don't send everything at once. If you've got a 10 gigabyte file, you don't send all 10 gigabytes in one lot. You might sort of stagger that, send a little bit, see how that goes, send a little bit more. Depending on the algorithm you have for that, it may change how much you send over a certain time period. It may be a constant. It really just depends on how that's implemented. And it might depend on how busy the link is, for example. You might send less when it's more busy. And so this is between 2 adjacent nodes. All right. Here's a data link layer example. Just draw this diagram, I think. There's a machine here, 67, and here's a machine 43. Machine 43 is the one that's sending the information, and they want to send it all the way to 67. So on this shared network, this pipe here or a bus, there's a source address and a destination address at the front of my frame in this case. Right, so that's the header information, and then there's my data, and then there's a frame check sequence. Now this looks suspiciously like the Ethernet model that we talked about in the previous lecture, so we can probably assume that this bar here is some kind of Ethernet link. Okay, so when a packet or a piece of information is put onto this network, it becomes a frame, and this frame has some characteristics, and those characteristics means that when it gets to here, this guy will look at, okay, 43 is sending it, am I 67? In this case, no. Do I need this message? No. Send it along. Yeah. Just as a question here, does that mean that this this communication is inherently insecure? Yes, everyone along the way sees it. Right, so there may be other things you want to do to make it more secure, like you might want to encrypt the information, for example, right? But based on this model, I'm giving it to everyone in between me and the final destination. Okay, so Here is an encapsulation example. So this is putting into the wider context. You'll see there's a machine A and P. And again, I think I will go back to the diagram because I can draw on it and make this a little bit easier to see. So machine A and machine P here on the end. They want to talk to each other. So A has some data. And okay, it's just data. It has to be encapsulated. Remember how we had this envelope model as we went through the different layers? So it has to be encapsulated or put together with the appropriate headers and trailers. And you'll see here that at this level, the transport layer, we add some transport information. We add this J and K aspects. Now they will be the port numbers on this particular machine. We'll talk about port numbers later, but when you get to a particular machine, you have a program running there. If you want to identify that program, you have to have a name for it, and the name in this case will be called a port or a port number. It's listening on a particular port. So the data is actually split up into two sections. You see it used to be one section. Apparently it was too big, so it's chopped up into two. It could be chopped up into many sections, and each section is an envelope. So each section needs the header information, in this case the port addresses. And J may be the port address on this side and K may be the port address on that side, for example. Okay, so once that's happened, we pass it down to the network layer, and you'll see that it's just the data, J and K, and then A and P are put on the front. Now what's A? A is me, P is them. So not only do I need to know which program or port to talk to, because there can be many programs running, I also need to know who I'm sending it to. They sound like different addresses. Yeah, you can imagine that as the port number might be like a unit address inside a block of units, and then the unit block actually has its own address that you can send letters to, for example, right? Okay, so once that's happened, you'll see that every packet or every chunk has its own header attached to it. So we have separate envelopes actually. And then at the data link layer, you'll see here that there's a header. This was some information, and then there's a trailer. This was the error information that we added. And all that stuff is just encapsulated inside for each frame at this level. Before they were packets, this time they're frames. Right? Now that goes through the internet, through the physical layer, and then what happens on the other side? It gets de-encapsulated, or unpacked is probably an easy way to say that, and we look at, okay, the header, is this for me? Yes or no? If it is, okay, cool. Send it up the chain. Okay, who is talking to me? Okay, and then which program are they talking to? And then it gets passed along. So it's a symmetrical model, all right? Okay, so that's showing an encapsulation example. I would just refer to it as packing it and unpacking it, basically. It's probably the easiest way to think of it. So the thing is split into packets. We add a network address. We add a trailer and a header. Reassemble the message on the other end. There's a whole lot of work that goes into this. And this is just adding that J is the source port address, where it's coming from, and K is the destination port address. And this is because when you have a communication, there are two parties, and you want to be able to identify both parties. If you want to respond, you have to know who you were talking to. So frame formats. There can be lots of different ways to package this information. So the header and trailer information can include the source and destination address, the error control information, something called a frame check sequence or parity, right? There's a number of these things that we could incorporate there. You might have the length of the frame, because potentially the frame can be variable size. You might have some sequence numbers, and a sequence number is like on a check, for example, where you have check number 1, check number 2, check number 3, and so you can uniquely identify a particular check in that example. And that means if you get two checks that both have the sequence number 3, you know that one of them is problematic, right? And we'll talk about sequence numbers later on, but they are actually quite useful in this environment. So the framing process may involve chopping the frame up into smaller parts. If a frame is too large, or padding the data if the frame is smaller than a minimum size. So we've seen that idea before, right? If it's too big, we just chop it up. If it's too small, we have to pad it out with extra information, whatever that is, so that we have the right amount of space that it's taking up. So here is an example. I think I've got a drawing for this one. This is a frame, or an Ethernet frame, for example. There's a preamble, and there's a start field delimiter, and then there's a destination address, a source address, there's a length, and the PDU, there's a protocol data unit, so that's the generic term for frame, packet, whatever. And then you have the data and potentially packing, and then you have this CRC thing, which is a error checking device in some sense. And now you'll notice there's a minimum length. There might be a maximum length because you have some variable length of this thing. There's a preamble, and the preamble is a series of ones and zeros, and then the start field delimiter looks like this. So if you've got a bunch of ones and zeros alternating, like 1 0 1 0 1 0 1 0, and then this start field delimiter is the last one of this, and it goes 1 0 1 0 1 1. Is that one slightly different from the previous 7 bytes of information? Yes? So what you can do is you can use that preamble to identify that you're about to get some information. If you see this pattern, lots of ones and zeros alternate, and then you see the 1 0 1 0 1 1, right, end, that's the start of the frame. So you can synchronize based on that information. Otherwise, how do you know when something starts? You're just getting a series of ones and zeros, right? So it's a nice way to identify that part. Okay, so that's a frame. It has some basic components, right? So at the very least, we need the destination and source address, for example. And then we have some extra things based for this particular format where we're able to identify the start, we're able to work out how big it is, and then we actually have the data and some error checking stuff. In terms of addressing, physical layer addressing identifies the actual network interface on the local area network. So this is different to, for example, the IP address of a computer. So when you have a networked environment and you have these TCP IP environment, you'll have an IP address, right? And there's IPv4, for example, you're probably used to. IPv6 is another version of it. That's different to uniquely identifying a computer on a network. So the way that works, there's something called the MAC address, which is a unique address which is based or configured inside your network card, right? So what that means is every computer in the world should have a unique number for this. And that means that if you have two computers on the same network, they won't conflict with each other. They have unique names. If they didn't have unique names, what would happen? You send a message to machine A, and there are two machine A's, you're going to have some problems, right? Okay, so obviously there's someone or something that looks after generating those unique names. There are some pieces of software where you can change those values. I just recommend that you don't do that in general because you're going to get some potentially problems on your network. And it's a MAC address, and it looks like this: 06010201.2C4B. Now that's a particular one. What base is that in? Looks like hexadecimal, right? Just from there's a B in there and a C. So let's go with hexadecimal, and that means that there are 1, 2, 3, 4, 5, 6 hexadecimal values, right? And each digit is a hexadecimal digit, right? So there's 6 lots of 8 bits. Okay. Physical addresses need to be unique on the local area network to which the interface is connected. I already described why that's what we want to do here. If you send a message to a network, you want to make sure it gets to the intended target, not multiple targets, for example. So there's a number of different ways to use this addressing model. Unicast, I can send to a particular machine. That's useful in a lot of ways. Multicast is useful in a lot of different ways, where you want to send stuff to a group of people or a group of machines. And then broadcast, everyone gets it. Right, so in this lecture environment, I'm broadcasting. Technically, I'm also multicasting because there's a subset of people in this room who are in this course. Yep, I am definitely not unicasting, right? Because there are multiple people here and you're all getting the information. If we were unicasting, it would be a one-to-one environment. The source address can only ever be a unicast address. It can only come from one place, is what that's saying. Okay, I think that makes sense. Here's an example of an Ethernet MAC address, and so there's a number of bytes, right? 6 bytes actually, and they're represented as hexadecimal digits. The last bit of the first byte is telling you whether it's unicast or multicast. So there's an example. So unicast, we said that the last bit of the first byte, so this is 4 digits, right? So 1000, and then this is 4 digits, 1010. This bit here is a 0, it means it's unicast. What about this one? 1000, and B is 1011. This bit is a 1, this is a multicast address. And then there's some information over here which tells you who the recipient's going to be, or who the recipients are going to be if it's multicast. Okay, so it's fairly simple mechanism. Again, just thinking about that in the context of computing, it needs to be simple, because if you're sending messages all the time, you don't want to spend a lot of time working out, what the details are. It should just be very quick to do that. Down the bottom, you'll see broadcast in red there. So what can you tell me about broadcast? If you converted that to binary, what would be the value? All once. So everyone gets it. That matches everyone. Does that make sense? Okay. So fairly simple but actually powerful model here. You can identify a single unit, multiple units, or a group of them, and then everyone. Moving on to transmission errors. So all communication channels suffer from noise and signal distortion that cause transmission errors. The bit error rate is a measure of how frequently an error is likely to occur. An example there is that a bit error rate of 10 to the minus 5 means that on average 1 bit in every 100,000 will be wrong. Now that sounds pretty good, actually, right? If you're walking down the street and you're like, every 1 in 100,000 steps I'm going to have a mistake, that's pretty good. In networking, it's not that good because you're sending a lot of bits, right? So you will get to that number very quickly. So depending on the type of cable that you have, Ethernet may have a bit error rate of in the range of 10 to the minus 10 or 10 to the minus 12. Okay, and so we will get errors. We can't avoid it, but we would like to minimize those, and we can do certain things to do that. One of the things we can do is we can shield the cable from interference. Right, so that's an example of what we can do to affect that. Single bit errors affect only 1 bit in isolation. Burst errors are the most common type of error, though, and they affect several bits, or even an entire frame, or maybe a minute at a time, depending what's going on in the environment. Right, so not every bit within that burst duration will necessarily be wrong. Right, so what you do is you measure it from the first incorrect bit to the last incorrect bit. Now that's a very vague definition, because it could be the very first one that you find, and then so you basically have to identify your level of concern in that sense. Single bit burst errors, we've seen this diagram before. 1 bit error at the top, it's very simple to deal with in a lot of cases. At the bottom, the burst errors are going to be more complex to deal with. So when we did the Hamming code stuff, we were looking at there's an error introduced. We can fix that as long as there is only one, at least with the variant of the Hamming that we saw, right? There may be more complicated ones which may let you do more complicated things. And so if we get a burst error, it's more problematic, right? We get multiple bits that are wrong. What we've seen so far, we can't address that actually. So we have two modes of error control. We have forward error control and backward error control. And forward error control transmits extra bits with each frame, and that enables the detection of any errors that are present. It enables you to identify their location and correct them. So you could, for example, here use Hamming codes. I already mentioned the limitation that we've seen. It's one error that we can fix. So if you get burst errors, you don't get much benefit from this. So burst errors are complicated to deal with. The other model here is backward error control. We just transmit enough information to know if something is wrong. And remember the Hamming distance, that was much easier to do, right? So when you get something, or you get an indication that something's wrong, you don't compute what's wrong and how to fix it. You just say, okay, give me another one. And in practice, backward error control is mainly used. It depends on the environment, but mostly you will do that because it's more efficient, right? It's expensive to send the information, or enough information to be able to fix things, and then when you get it, you first of all have to detect it, and then you have to try and fix it. Yeah, so it's just easier in general to send it. Now there may be some application where you do want to send extra error information, right? So, but in general, it'll be the backward error control. Flow control. If the sender is able to send frames faster than the receiver can process, it will overflow the receiver. And you can imagine this in a normal, speaking environment. If someone speaks way too fast, you can't understand. You start dropping words basically. And so, two approaches are there to solve this problem, at least on this slide. The sender can send a single frame and waits for some acknowledgement of receipt from the recipient. And this is like that polling model that we talked about, where I'm going to ask you, do you have something for me? Do you have something? Yeah, right. That's one. That's the polling example. In this case, I'm going to give you some information, and I'm just going to wait for you to say I got it, and then I'll send you the next one. I'll just pass out one little bit at a time. The other one is that we can come to some kind of agreement about how fast we communicate. So I could send you one packet, and you say I got it. Then I could say, okay, look, he got one, all right. So I'm going to send two. Got them. Three. Got them. 4, 5. I get to 10, for example. Maybe I don't get the acknowledgement for 10 of them. And then I go, okay, I've got to back off. 10 was too much, and we can adjust. Now, some of them are fixed, some of them are adjustable. There's one called the sliding window protocol, for example, where you can adjust the window of frames that you have. So there's a lot of different ways to do this stuff, but that's the general idea. So one of them is send one thing and wait for acknowledgement. It's very tedious and slow, but it's effective, right? You will know straight away if it didn't go through. If you send multiples, well, some of them may have got lost, and then you have to reconfigure that. Now we move on to medium access control. So this is a reasonably big section, and it has a lot of the different protocols for multiple access on a network. So when you have any multi-point configuration network where a number of devices share the same communication medium, then you need some way to control access to that medium. It's shared, right? If you don't control access, then you're likely to get those. Remember the diagram I drew with the car, I think, where the car, there's two cars and they hit each other and there's synchronization issues. You've got a shared thing. In that case, it was a bridge, and if you don't coordinate the sharing of that bridge, you're going to run into problems. And there's different kinds of problems that can happen. And so in this environment, when we're talking about the medium access control, we use our method to determine which device can transmit data at a particular time. And what we want to do is we want to avoid packet collisions. We want to avoid those cars hitting each other, actually, because the outcome of that will not be what we expect or intend. There's three basic categories of these multiple access protocols. You'll see here there's a little table there. Controlled access, random access, and then channelization or multiplexing. We've seen multiplexing before as a circuit, and we'll talk about that at the end of this section. So the first one we have is controlled access and then random access. And you'll see there's reservation, polling, token passing. This might be the Bluetooth kind of variant. Random access might be Ethernet, MA, CSMA, CSMA/CD, CSMA/CA. Can you see a pattern there in the names? Yes. So they're a particular model, and then there's some variations on those, right? And then the channelization, multiplexing, 3G, for example, FDMA, TDMA, CDMA. Again, there's a pattern in the naming, so they're related in some sense. So we're going to go through each of these. So like I said, there's quite a number of them, but they fall into categories. Right, so think of the categories as a starting point. So controlled access, or before we go into that, let's have a look at the shared access architectures. There's a bunch of different diagrams here that illustrate how you can connect machines. One of them, the top left, is a bus. There's a switch at the bottom. There's something called PicoNet, which looks like a wireless kind of environment with those laptops there. There's a master and slave model there as well in that PicoNet example, right? So then maybe there's one big machine or one boss who coordinates everything. And then there's a distribution system with access points and servers, and more complicated system. They're all shared access architectures, and they all need to coordinate how and when people can use that medium or the shared medium. So controlled access protocols. So now we're in the controlled access part with the reservation, polling, and token passing. In this model, we want to avoid collisions completely. So polling, or the master-slave model, this is a pretty obvious one. If there's a master and there's some slaves, the slaves don't get to do anything without the master's approval, right? So the master is the central control point. It's centralized, easy, yeah. And so the central primary station selects the computer before sending data to it, and it does polling, basically. It asks them, do you have anything for me? And the computers that are not the master don't do anything without being told they can, right? So there's some coordination there. So it's simple, but it may not be that efficient, right? Remember the polling model we went through in the class where I asked everyone, do you have something for me? Do you have something, right? That could, by the time it gets back around to you, you may have been waiting for quite a while. Then we have the token passing or token ring model. This is another very simple model, I guess, in terms of you probably have used this model before. Whoever has the token can talk. So if I say, okay, here's a coin. If there's only one coin and you have it, you can talk. If you don't have the coin, you can't talk. So the coin gets passed around in that case. In this case, it will be a virtual coin. And so basically, there's each computer takes a turn transmitting, and that turn or the coin is passed around the network from computer to computer. The most common form of this is the token ring local area network, and there's a software token that's passed around in a circle. There's some problems with this. If you counterfeit the coin, you copy it, then two people have a coin, for example, you could lose the coin and no one can talk. You could not give the coin to the next person, so you're the only one who can talk. Again, there's a lot of different variations on what can go wrong here. Last model there is reservation, and that's basically is the time is divided into chunks, and you can reserve a slot in these chunks, and you can say, I want to talk. And if you've reserved it, then you get that particular time slot. And so you can think of it as like a box with some slots in it, and you can put your message in a slot as long as you have asked for that slot, for example. So here's some examples. I think I will just go to the drawing here. And so polling master slave, I already mentioned it, or I described it sort of just using words. This is a visual example of it. Here's the primary, the master in this case, and what they're doing is they're looking at B and they're saying, I want to talk to you. And this one says, okay, I'm ready to be talked to. They give an acknowledgement, and then I send the data as the master, and they say, I got it. They're completely passive in this example, right? They are told, I want to send you something. They have to respond and say, yes, I'm able to do that, and then the transfer happens. The other example here would be if the master says, okay, do you have anything for me? And they say, no, negative acknowledgement. This one says, data. So if you get data, that's not a negative acknowledgement, which means, yes, I've got something for you. I don't even need to say, yes, I got something for you. I can just start sending stuff, and as long as it's not a negative acknowledgement, you will recognize that it's data. And once I've got it, I'll tell you, okay, got it. Okay, fairly simple model. It's pretty powerful. Again, may not be so efficient, right? Here's the token passing model. So there's a ring or a loop here, and one of them will have a token, and it will get passed around this ring, right? Okay. That's the token passing example. Like I said, it just gets passed around. It's very simple. Again, may not be so efficient, right? Because you might have to wait a long time for the token to make it back around to you. Now we move on to the random access protocols. MA, CSMA, CSMA/CD, and CSMA/CA. You'll see on the bottom there how they're actually configured. MA is the parent, CSMA is a child, and then there's two children, CD and CA. So there's no centralized control over who gets to send the data in this environment. The protocol needs to solve some problems. When can the station access the medium? What can the station do if the medium is busy? How can the station determine the success or failure of the transmission? And what can the station do if there's an access conflict? These are the kinds of things you would want to be asking about if you're all able to talk at the same time. How do we deal with these situations? So there's 4 contention-based protocols here. So the first one, multiple access, or MA, was Aloha. It's developed at the University of Hawaii in the early 70s. That's a really long time ago. Right, so they were looking at this stuff actually quite a long time ago. It's not necessarily a recent innovation. It's designed for wireless local area networks with 9600 bits per second data rate. That's very slow by our standards, but in the 70s that was probably very fast. All right, and it's based on 2 main rules: multiple access and acknowledgement. So multiple access, any station sends a frame at any time when it's ready to do so, as long as it has something. And there's an acknowledgement. After sending a frame, the station waits for acknowledgement. If it doesn't receive it within twice the propagation delay to the base station, it resends the frame. So what's happening is, I'm here and I want to send it to you. You see there are 2 links. This is why we wait for twice, the distance in this sense. So That sounds good. There we go. So there are some collisions in this model. We haven't really dealt with those. We can say they can do it at the same time, but if there's a collision, what do you do? So if you have a collision, it will significantly reduce the performance. Right? You're taking up the channel space, and you're also going to have to redo it, right? Because the information is garbled. So CSMA attempts to reduce collisions by having the station sense before transmitting. So in this case, it listens. So it says, okay, is anyone talking at the moment? And if no one's talking, I can start talking. I'm sure you do that in the real world as well, where you have a conversation with someone and no one's talking, and then you start talking and they start talking at exactly the same time, right? So you can try and avoid this. It will reduce but not eliminate the collisions. And in this case, it's not exactly like the in-person example I showed you there. But why will it not eliminate collisions? Well, if you look at this example, it's time 1 here, and A is listening. Yeah, or up to this point, it was listening. There's nothing happening. Actually, Z may have started sending something, but because they're a long way away, I'm not actually getting their signal yet. Yeah? So there's a timing delay between when they've done it and when I hear it. So if that's the timing delay, can I guarantee that there's nothing on the channel? No. I can reduce it, right, because I'm not going to start transmitting if someone's actually talking, but there's still potential issues. So CSMA CD and CSMA CA, carrier sense multiple access with collision detection, it's got a mouthful, and then carrier sense multiple access with collision avoidance. So there's 2 different strategies to work with here. Detection, the workstation checks whether a collision has occurred, and if so, it resends the packet. This is like traditional Ethernet. Carrier sense multiple access with collision avoidance. When the station finds the line free, it waits long enough to increase the probability of avoiding the collision, right? And then it waits for acknowledgement. If there isn't one received, then it resends the data, and this is the Wi-Fi kind of a model. Okay, so slightly different variants on this. So why would you have CSMA/CA, collision avoidance? The reason is that wireless local area networks can't implement CSMA-CD because collision detection implies that the station must be able to send data and detect collisions at the same time. It may, in theory, be possible, right? But in practice, that may be too expensive to implement, right? So collisions can also go undetected because of hidden terminals. And so I can probably draw this probably very badly, but here is A, here is B, and here is C. Alright, so these are network towers, for example, and they're able to see each other and they're able to communicate. There are various distances, so we have the same problem where C can start talking but A can't hear it yet, for example, until a certain amount of time has happened. But imagine that a big truck, really big truck, right, here it is, sitting in the way. Let's say this is an armored truck. Now, there's a lot of steel in an armored truck, and it will interfere with the signal. So actually, you can be transmitting, and I may never get the signal because the signal is now too weak because this truck is in the way. Right, now, obviously, that's a contrived example, but you can imagine that there are various reasons why signal strength may fluctuate, right? So if you have this situation, can I tell that C is transmitting? No, not possible. Now, sometimes I might be able to, but in that example I can't. So that could happen because the signal is completely blocked, or it might be too weak, for example, and again, that can happen for various reasons. So in this case, you can't implement CSMA-CD. You're going to have to work with the CA variant, the collision avoidance variant. Now we move on to channelization. So in the previous approaches, the medium is treated as a single channel. So the alternative is to use the medium to create multiple subchannels. So we're just going to split the channel up into chunks. It's a little bit like that reservation model where we had separate slots, and we can just use those slots. So multiplexing allows a medium to be shared by many simultaneous channels. There are 3 basic approaches: frequency, time, and code division. So FDMA for frequency, time for TDMA, and code for CDMA. So you'll see on the left there's a mux or a multiplexer. Has multiple inputs coming in. There's one line between that and the demultiplexer on the other end. and so you compress those signals into one stream basically, and then the demultiplexer on the right hand side uncompresses that stream. There's different categories of multiplexing. This looks a bit busy. It's actually not as bad as it looks. There's analog and digital, so frequency and wave division, and then there's digital code and time division. So we'll go on to time division multiplexing. So the channel is divided into time slots, and each user is allocated a slot, whether it's empty or not. Right. So if there's 5 things, you've got 5 slots. Everyone has their own slot, and it just repeats 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and so on. And so the multiplexer has to take, in this case, 4 signals and allocate them to the appropriate slot. There's some timing involved here, for example. Let's see if I have a diagram for this one. Yes, so the top one here is the timing one, right? So basically 4 things coming in. One is this slot 2, 3, 4. The previous cycle it was 1, 2, 3, 4. The previous one is 1, 2, 3, 4. It's just going to do 4 in a row, right? One for each slot. There's a variety of ways to do this. We'll talk about those later, I guess. But frequency division multiplexing splits the total channel capacity of bandwidth into several smaller channels using a different carrier frequency. That sounds very technical. You're very familiar with this model, actually. Think of a radio station, right? So when you get a radio station, it's at a particular bandwidth or a frequency, right? And there are radio stations around it, below and above it usually, right? Now, what's happened is you've got a radio station signal, and they have boosted it to a particular frequency range. And everyone gets their own variable boost. So one might be boosted by 100, another one might be boosted by 110, for example, and they're separated, right? Because your receiver can receive things at different frequencies. And so an example of this frequency division multiplexing is a radio station or a bunch of radio stations. So if you're looking at the left there, you'll see that there's a yellow, a blue, and a red next to the telephone. They're different signals. And what's happened is they all start at 0, for example, and then they're boosted up to their particular level that they need to go up to. So you have multiple things happening at the same time, but they're separated in some sense, and you can grab them based on that separation, right? Wave division multiplexing. Well, it's exactly the same as the radio station model, except now we're using light, right? And so there's just different frequencies that we're working with, and so you have the things, and they're, you know, configured in a particular way so that we can unpack them on the other end. Okay. Code division multiplexing uses special codes to share a single channel, allowing all stations to transmit simultaneously using the same frequency range. So this is a little bit more complex to think about, but if you think about it in terms of every station that's transmitting has its own unique name. And we can use that unique name as a series of bits, for example, right? And if I have my own unique name, then I can attach that to the message, and I can identify, okay, it came from this one. Yeah? And so it's based on either using different frequencies for frequency hopping, and the transmitter might jump to different frequency bands every few milliseconds while transmitting the data. Yep, it's possible. Or using a different fixed set of unique code words for each user, each station. That's the one I just mentioned, where you just have your own name and you attach that to all the messages. And as long as your names are unique, right, then you can uniquely identify those things. So basically you're tagging it with, you know, a tag of some kind. And that's normally used for wireless networks. So here's a question for you, just as a general thing. Who invented the idea behind CDMA? There's 3 people there. So was it the Mad Magazine guy? Was it Hedy Lamarr? Or Irwin Jacobs? Who do you think? It's Hedy Lamarr? Okay, so some historical background, I guess, in terms of that. So a long time ago, they actually were looking into this stuff. And I guess it's an interesting thing that historically we don't hear a lot about these people. Right, so in terms of, you know, historical figures, we hear about Bill Gates, for example, you know, so, you know, but there's a lot of people who have done a lot of interesting work who are not necessarily that famous for that work, right? I thought that was interesting to put in. So What we looked at in summary here was we looked at the data link layer, addressing, transmission errors, and medium access control. As I mentioned earlier, there's quite a lot of stuff there. If you want to drill down into some of that stuff, like the way that some of those medium access control things work, it's actually quite technical, quite complicated. It's interesting, but it's enough for us to understand at this level that there are different models and what some of those models are trying to achieve, right, and how they go about doing that. That's basically what we had to look at there. Next thing we'll look at will be internetworking, and that's the end of this section.